Alright, welcome to another AQA A-level chemistry video. It's been a long time now. I am back. I was doing a lot of videos on inorganic chemistry or the year one inorganic chemistry. If you need help with that or the exam questions related to that, check out the previous videos. I'm not going to leave a link in the description because you can just go to the playlist that I've left. Want to leave a link to the playlist? Maybe. If I don't, then I'll just sit here. Just go to the channel and do that. But yeah, I'm going to go straight into the video now. I'm going to be talking about acylation. This video is about, acylation in general is just about making the chemical way of forming esters. And it involves nucleophilic addition elimination reactions. And yeah, I'm going to go straight into the video. So acylation reactions can be used to produce a variety of organic compounds like amides. The compounds below are just a few examples of acylated materials. So I have amides, acyl chlorides, and anhydride. And these can all be examples of acylated materials. So what nucleophilic addition elimination is, so the nucleophilic addition elimination reaction happens with acyl chlorides and I sort of kind of want to go, but these are compounds that can be involved in acylation reactions. Just I didn't want to just brush through that and not kind of explain here. These are just compounds that can be involved in acylation reactions. So anhydrides, acyl chlorides, amides, they can all be converted or used to make to form esters for esterification. And the reaction that they do is called a nucleophilic addition elimination reaction, and that happens between the acyl chloride or could be an amide or an anhydride, and it's used to produce amides, or it can be used to produce amides, carboxylic acids and esters. So it's not just esters. I should have clarified. You can form amides, carboxylic acids, and esters. But the ones that's usually, I mean, I say one that's usually could be forming a carboxylic acid, but the one that's I've seen quite a lot is esters, and I'll be going through the mechanism here. As I said before, how I, shout out to Dr. Bakari when he says to me, and I always remember this every time whenever I think about mechanisms. If anyone ever gets confused about what mechanism you're doing, or you're kind of confused about what's going on in the mechanism, always look at the name. Always look at the name. Even if you might get an example, the usual example that you get in your exams where they'll tell you to draw out your mechanism, and they'll say name and outline the mechanism. That's always what they say. Name and outline the mechanism. The whole thing's probably 6 marks. 1 mark for naming, and then the other 5 marks are for the actual mechanism itself. And if you ever get confused about what the name of the mechanism is, or you know the name but don't know how to do the mechanism, it's always worth knowing out what the name actually represents. It's just saying what is actually going on in a reaction. It's meant to be self-explanatory. It's one of the very few things in science that are quite easy to understand. It's just saying it's a nucleophile that's being added, and then what's going on in that compound, so another group in that compound is being eliminated. So you have a compound, and a nucleophile is being added to that compound, and another group from that compound is being eliminated. That's it. So I'll show you here. So in this case, we have methanol being added to this ethanol chloride. We call this compound ethanol chloride. That's being added. Then the methanol is a nucleophile. So this nucleophile is being added, all right? And then to skip forward, in this reaction, we're losing chloride group. So this chloride group is being eliminated. Actually, we're losing HCl. Actually, we're using a H plus and a Cl minus. Obviously, HCl is a very strong acid, so it will just dissociate back into H plus and Cl minus. So technically HCl, but really it dissociates. So you just call it H plus and Cl minus. But the idea being that you're adding a nucleophile here, and you're losing groups from the original compound. Nucleophile added and elimination, and that's it. Always you have to know that the arrows where they go, but the essence of what it is self-explanatory. I'm going to shut up and I'll actually explain what the mechanism is. So the nucleophile is being added, as I've already said. That's where your Mark 1. Mark 1 comes from drawing an arrow from, so you have M1 will be just doing this part here. If I had it in green pen, right? This would be M1. An arrow from the nucleophile to the central carbon atom. M2, I believe, would be the second arrow going from the double bond in the between the carbonyl group to the oxygen. The third mark would be from first of all, what's actually happening. I'm going to explain what's. I think I should explain what's going on first before I actually go and show the marks. But the nucleophile is being added, and when that happens, you can't. The carbon can't have 5 bonds. I'll explain the marking system later. But the oxygen is bonding to this carbon here, and obviously this carbon already has 4 bonds, right? So it needs to lose one of them because it can't have 5 bonds. That's unstable. That's a very non-polar bond. That is a polar bond, but this carbon oxygen is much more polar, so it's more likely to lose this one of the bonds from the carbon oxygen first, and it will form a CO single bond with a charge. So and that's what you form here. So you have a CO single bond and oxygen, and obviously oxygen here, but this oxygen is now charged because the oxygen is very electronegative. It likes to have this charge. It wants to form this double bond here. It wants to desperately reform this carbon bonds here, and if that happens, well, as I said before, carbon can only form 4 bonds. It can only form 4 bonds. So if that reforms here, then something needs to give. And what happens is that you could lose this. That can happen. You can have the oxygen just being this bond breaking here, because this oxygen here is also very this carbon oxygen bond is very polar. But then you're just left with just this again. Like you're just losing this bond again, and nothing's really happened. You just reformed what you had in the beginning if you break this bond here. So what actually happens is that this carbon chloride bond actually breaks off instead. Obviously this can happen, or you can break this one, but interaction more favorably in the mechanism, you'll break this carbon chloride bond because it's quite a polar bond. It can lose this, it'll break. When I mean polar here, if anyone doesn't realize what I'm saying, is that chlorine is quite electronegative, so the electrons in this bond are more closer towards the chlorine, and they're more attracted to chlorine, and so the electrons aren't in the center of this bond here. The electrons are actually more close to this chlorine here, and it's quite a big compound as well. This is a better leaving group. In essence, it's a better leaving group. To cut a long story short, right? If any teachers are listening out here and I've said something wrong, shout me then. But that's how I always understand it, right? So always make sure to have your charge here. That's always very important. Your lone pairs here. This is a very non-polar bond. And also here, we discussed how this would be a leaving group. So this oxygen will reform the double bond with the carbon. Because remember, it really wants to reform that double bond, and the chlorine is a good leaving group, so that will go, and it goes from the electrons here to the chlorine. As I said before, chlorine is quite electronegative. Now, there's another thing here, is that oxygen only likes to form 2 bonds, not 3. So it has this CH3 bond here, so this methyl group here, and then obviously the rest of this group here. So it's positively charged now, so what it needs to do is it needs to regain that. The easiest leaving group here is hydrogen, so it will break this bond. The electrons would go towards the oxygen, and then H plus will be released. And then when that happens, now you now have your ester. So, and then obviously if you pause the video now and try and name this compound, if you pause the video and you've answered the compound, I'll just say what it is. It's methyl ethanoate, just simple methyl ethanoate. It's always the name of your, just remember, it's always the name of your alcohol. Is the first part, is the prefix, and the suffix is the carboxylic acid. I know this is the carboxylic acid because it has the carbon group here, and this only has the oxygen group here that would have came from the hydroxyl group. So this is methyl because that's coming from the alcohol here. Ethanoate. Great. Should I write it down? Yeah, I'll write it down. Methyl. There's no extra side groups here, so I can just call it like that. Right, now coming to the marking point of this, right? Oh, did I do something there? Okay, cool. I said for the first mark will come from this, from the lone pair on oxygen of the methyl group, the lone pair on the hydroxyl the lone pair on the oxygen on the hydroxyl group of methanol going to the carbon, central carbon atom. The second one will go to, the second mark would come from you showing that you're breaking the double bond in the carbon of the group. The third one will be from, first of all, it'll be from showing the oxygen needs to be charged. The oxygens need to have their own charges. So M3 will be showing that the oxygens are charged, and then they have bonds going here. So negative charge, positive charge, lone pair as well. M4 will just be showing, in the mark scheme, M4 is generally given as so M4 would be the arrows, so they're all going in the right direction from the lone pair here to this carbon here to the bond here between the carbonyl, and then from the bond here to the chlorine, and then from just, you know what I mean, the arrows. Make sure the arrows are correct. M5 isn't for this. They never actually give M5 for this, even though you should always write this, always. M5 is for actually, you won't get it correct. You won't get it correct unless you write this part here, obviously. But M5, what actually is for showing this intermediate, and pretty much I kind of get that point, because if you can show this intermediate here, you've pretty much shown that you can get it to this point here, because you know if you've done that, and that, you're gonna get that anyway. But that's how they do the marking system for AQA in terms of the mechanisms. Did I research it? No, this is just playing from memory. If I have missed something out, if I've missed something out in the marking way, I've at least shown it in the way I've done it. And yeah, so I'm gonna go skip to the next part of this now. So mechanism, right? So this reaction can be done with water, ammonia, as a nucleophile. It doesn't have to just be an alcohol. It could be water or ammonia, because they're both nucleophilic. And yeah, so I mean, ammonia can actually be both nucleophilic and, can it be both nucleophilic and ammonium? Ammonium is electrophilic actually. Never mind. Yeah, sorry. Water, ammonia, nucleophiles. There you go. That's all you need to know anyway. Yeah. So industrial uses of I don't know why I keep saying actuated. Acylated. There you go. Industrial uses of acylated molecules. So acylated molecules have many uses in industry. And one thing you need to know understand is the dangers of it. So ethanol chloride, which is what this compound here is dangerous. It's actually quite a dangerous material, because if it gets wet, it will produce hydrochloric gas, which can burn the skin. It's a skin irritant, and it's very painful. So this is what we do as a solution. Is in industry, and more generally in labs, where you use ethanoic anhydride, which is this comma here, ethanoic anhydride 1,2,1,2, and it's just an anhydride here. And this is generally more safer. It's easier to store, and that's the advantages of it. It's less reactive than your acyl chloride. It is less reactive, which is a disadvantage, but the overall benefits of it being safer to use, easier to store, less reactive. I mean, less reactive means it's easier to store actually. So which is a benefit of it. But safety is always, remember when you're talking about safety of anything. If you get this can come up as a question when they ask you, why would you? They might ask a question like saying, I have seen it before. Why do they not use acyl chloride in a lab, or ethanol chloride in a lab? Why? And first of all, they'll say, why would you not use ethanol chloride in a lab? And what would you use? What would you use instead? And what are the and why is that more advantageous? So you're talking about the hazards, the hazards of what it is, why it's useful, and why it's safer. Obviously, what's been done. So, for example, here, so the ethanol chloride is dangerous. Or I just said that part here. In industry, in more generally labs, we use ethanoic anhydride, because ethanoic anhydride is slightly less reactive, but it's much safer, and because it's more, first of all, it's more stable. So it's more easily stored. And it's cheaper as well. Cost is also another thing that you want to talk about. Cost isn't really to do with safety or hazards, but more when you're talking here, more talking about this is a problem, or if you're going to talk about it being a HCl gas, which can burn, say that you can do this reaction in a fume cupboard. That's something you could say. So you could just say it's a gas which you put, or irritative gas. So do reaction in a fume cupboard. But generally, this reaction is done. Sorry, I didn't like that. Yes. Generally, when you're doing this reaction, at least in school, I mean, I don't think you've done this in school, but you'd use ethanoic anhydride because it's just much safer, easy to store, and you're still getting what you need. So this is definitely a reaction that you do for. It's one of your required practicals, making aspirin. But aspirin is the example of an ester. Yeah, you definitely do this reaction. Yeah, I remember. I don't remember what the practical name was. I don't remember what number it was. But making aspirin is one of your required practicals. So I'm not doing required practicals on this channel unless it's desperately in demand. But aspirin is an example of an ester made with ethanoic anhydride. The final step in the synthetic is the synthesis of an esterification reaction, and this is depicted, I should say, below. Not above. It's not below. It's below. Moved that. It was originally here, but now I put it here. But yes, this is basically what you have here. So you have your what would this be? 1, 2 ethanoic acid. Yeah, you have your ethanoic acid here, and you would have your I forgot the name of this compound, but this here is aspirin. This here is this here is aspirin. Yes, this here is aspirin. And I forgot what the name of this compound was off the top of my head. Anyway, I'm not doing the required practical here. Today's not about talking about the required practical. You do need to know the name of this and this when you're talking about your practicals. You go through that. But I'm not here to talk about practical. I'm here to talk about the actual chemical reaction that's going on in the actual nucleophilic addition and elimination. You have your essentially your carboxylic acid here, and you have your nucleophile. That you have your nucleophiles here. And all I want you to do, right? And this you can form either this, and you can form either this. These are the two things you can form for your reaction. I want people to do so. Actually, this is the one that's actually acting as your. So make sure that I don't incorrectly say something here. Yeah, this here is reacting with your your carboxylic acid, then this would be actually acting as the nucleophile, because it's the one that's actually acting as the alcohol here to get this reaction. So I got this from Seneca Learning, so bear with me. This is the example here. I'll make you do both examples just to show you, but I want you to try and form this compound here. First of all, I'll do it with both to show you can do it with both. I'm pretty sure this is the one as aspirin. I should have checked beforehand. I really should have checked beforehand. But sorry about that. I just need to make sure for certain that this was aspirin, because I did form this compound as well. But this is aspirin. Yep. That is a compound that you should be able to identify when, especially if you do, it's a required practical. But yeah. All you need to know is that this forms with this, and you need to know how the mechanism actually works. Which is an easy mechanism to do. So I've already showed you how to do that before. I can now move over. Now I've shown you what the compound is. I can actually just go straight to here, here. Go from here to here. Remember, as I said before, the nucleophile to the central carbon atom here. I should have done this in the center. Actually, can I move this? Can I move this? I can. Beautiful. Right. That goes to there. You now form this intermediate here. That's a way massive. I assume, by the way, that you've paused the video now, you've tried to do this by yourself, and you've gone through it now. If this is going way too slowly, you can just skip to the end where I actually explain it if you already understand what's going on. But I'm just going to show you how how I see it. So, you can just, you know, if you can't do it at an angle, you can just do it straight up, because it makes it easier for you to see exactly what's going on. OH here. Yes, CH3. So now that we've formed this here, remember this is a positive charge now because it's got 3 bonds. This is more, this bond here. Actually, I can elongate this bond a little bit more just to make it easier for you to show your arrow. I'd go from there to there to show that. That's happening there. When that happens, this is the best leaving group. Actually, separate this out a bit more. It makes it a bit easier to show that it's the oxygen that gets there, not the hydrogen. I can move on now here. Oh, I mustn't forget the compound, the extension group here. Mustn't forget that is part of our compound, so we shouldn't neglect that. That is, I mean, that hasn't changed at all. I mean, it's not even involved really in our reaction. Really, I could call this whole thing here R, but obviously for the purpose of the reaction, and AQA always wanting to show that this compound is still here. But really, I mean, at least in A level, when you go to higher education, you can just represent this whole thing as R because it's not really involved in your reaction. The only part we actually care about when it comes down to our reaction is the forming of this ester group here. O still remains here. C double O CH3. And then obviously that's the leaving group here. You've actually kind of formed water really. You formed water as one of your byproducts. You have a H plus and an OH minus, and you don't have to actually represent the H2 here, but yeah, that's what I have here. So now this is pretty much the same compound. This is just inverted. It's just inverted. It's been rotated because it is a 3D compound, obviously. So it's been rotated in space, but same thing. It's the exact same thing. If you was to, I don't know how many degrees you flip that by, but it is literally the same thing. And yeah, that's all it is. And this is aspirin. That's it. Hopefully you found this video helpful. I'm done. I almost forgot that I said I was going to do both of them. I'm a man of my word. Can never cap on beats. Can never be me. Yeah, so I'll do the other one. I'll do the other one just to show you that this is the one you need to know. I mean, at least you need to understand how to get to this point here. But just to show you that there's the principle behind it between nucleophilic addition and elimination. What was the original compound looking like? So we had something like that. I believe. Yes. Yeah, if I get the same compound right. Yeah. Okay. So why do I always do this part here wrong? Here we go. This part goes here. There. So it's a bit scrappy. I should have made it a bit more. Can I actually? Maybe I can just move this a bit further down. Splendid. Yes. All right. So can move this down here. So the lone pair on the oxygen of the alcohol going to in this case, this is the one that's acting as the nucleophile, by the way, because this is the carboxylic acid. That would be acting as the, I guess, the electrophile in a way, because the carbon will be slightly partially positive charged. You have a partial positive charge in a way. This is partial negative. You don't actually have to represent the charges, but just for the sake of showing you this reaction here, this is that acting as the electrophile, as the nucleophile in this case, because it's the alcohol that's reacting to this carboxylic acid's central carbon atom here. When that happens, you then have this is better. I mean, for the sake of it, should I go and just call it R? Because technically, I can call everything from here, right? I could call this R. And call all of this R, because it's not involved. This is the only part here that's actually involved in our reaction. The rest of it isn't actually relevant. But so I'm going to try and do it the same way that as you do it in an exam. Because unless they specify that, you can just call it R. Make sure it goes all the entire way. All right, so O, they're negatively charged. This is technically just an OH that can be you have your OH here, hydrogen, oxygen there, and then CH3. Also do it a lot faster than the way I'm doing it. I'm just making a lot of mistakes. Make sure that I don't make mistakes here when I'm drawing it. Yeah, so that's gonna reform there. That's a better leaving group. This is positively charged here, so that can only have 2 bonds now. And now we just have the case of our, I mean, technically this looks like an anhydride, really. It looks like one. Well, it's not actually, because you have this massive phenol group here. But yeah, ester bond here. This is, no, I'm not gonna make an assumption what that type of bond is here, but you can see what's been formed here. You can see what's been formed here. Is this an ester bond card? I forgot when you have a carboxylic acid bond to another carboxylic acid. I remember this has a name. But yeah, as I said before here, I'm pretty sure it's called anhydride. But anhydride has to be the same on both sides. But either way, the idea was to show you that you can do the same thing for both sides. But that is how a nucleophilic addition elimination reaction here. Look, nucleophile added. I've lost the hydrogen. I've lost an OH. I can form water here. An OH and a H plus, an OH minus and a H plus been lost. That's it. There, I'm done. That's it.